Before we create our logic, we need to be able to display it. So we're going to create our logic here. And the results, we'll call it Q for now. We'll go into another area called our load circuit. So when the Q is equal to a 1 or a high, we want to put an LED on. To do that, I've decided we'll do things this way. Our Q will come into here into an nMOS. Out comes the answer. Another VDD here. We can use a different power source. Now we want to drive our circuit. This is our LED symbol. This is a resistor. So what happens here is if this is a 1, and the answer, as you know from before, will come out a 0 here. And if we put a 0 in here, the answer will come out here as a 1 or a high voltage. And this voltage here comes from VDD, and it'll drive through a resistor or a pull-up resistor, I would like to call it again, into an LED or light emitting diode. We need this resistor here, otherwise too much current will go through this LED and it'll blow. And this resistor will do about 220 ohms. And this resistor up here will do 220 ohms. So now we'll construct this, and we'll use Multisim first to simulate the circuit and design the circuit. We'll label this one here, drain, gate, and source. And this is source, gate, and drain. So we'll head off to Multisim now. Multisim is a simulator we will use to design this actual load circuit and test it all out before we start creating our digital logic. So when you first start Multisim, get a default screen like this. We won't be using this initial design, it's a blank design, it's not based on anything at the moment. We'll close that one and we'll open up a new schematic, and we'll base it on the NI Elvis breadboard. You can do blank if you wish, but we'll use NI Elvis because I've got the actual board here and we'll be doing the construction on that. Multisim's a program that comes from National Instruments. So first off, we need to place a couple of resistors. That's 220. One, two, and we'll place a third one there. I'll show you in a moment. Then we also need to do our light emitting diode that we talked about before. And we'll do a red one. There's our red LED. We'll place that down there. And then we'll need ground. And finally, we'll go and we'll place a switch. I think it's under basics. There it is. We won't use this switch when using the digital logic. But this one's just to prove that our logic for creating the load circuit works okay. Single pole, single throw. I think that's about it for now. We'll rotate that one. And now we need our CMOS. Not CMOS, sorry, transistor enhanced. That's the one. And we need our pMOS. And from memory, ZVP. There it is there. I'll stick that there for now. Close it. Now we want to look at our symbol pin names. So now when we zoom in, we can see our drain, gate here, and source. We'll do the same for that one there. I thought I did it actually. I haven't used Multisim until a few days ago, so for you purists out there, I'm not that great, but I'm getting better. Now we have our source at the top for the pMOS, and we might just name that one QP load, and we might call this one Q in load. We can change it later. Alright, I'll quickly show, no, I'll draw this up first. When we press the letter L, we're going to switch this value on. So I'll tidy it up later. Switch there. That goes off the ground, if you remember. Rotate that one. Zoom in a little bit. Remember, the answer comes out here. And then we're for the pMOS. Third time lucky. This is our load, which we're going to drive this LED. And this one again goes off the ground. Use this ground. Starting to come to peace. Now we need to drive this whole circuit. So we've got a 5 volt here. It's our VDD. I think that's about it. Run it. Great, everything works straight off the block, which is fantastic. So I'll quickly cover off what's happening here. Our power, this is also known, you can call this VDD. We're applying power to the resistor here, 220 ohms. And when the switch is closed, we'll drop it down and go straight to ground. When the switch is open, we'll get a 5-volt across here, and that'll drive our answer to our load, the pMOS load, which will drive our resistor, and we'll call this R load. RL for short. And we've got our LED, and we'll keep that with LED 1. And this one is for resistor for the nMOS, which we said is important. And this is the resistor for the switch. If we don't have the resistor for the switch, what happens, we'll drive all the power back down to the battery or the power source, and we'll short circuit things, so this is important. So we'll just make a little note here. I think we can do it here. Place comment. When switch is closed, 0 applied at the date. I'll improve that later on. What I'll do is I'll just tidy up on this, but this is our load. I better save it as such. Where shall we save it? Education, courses, digital logic, labs, part 1. We'll call this load. Make sure it's saved. Right, I'm going to go away and tidy this up, and I'll show you the tidied up version shortly. I'm back now. I've tidied this up a bit. What I've done is I've connected all the grounds like this, and in here what we did is we found a power source called VDD, so we connected that up to 5 volts, and then we've got 5 volts here and 5 volts here as well. Also, what I did is I changed the package details. I'll just find it. To fit TO922X, so it looks better when we're drawing it up or designing it on the breadboard, which I'll quickly show you now. By changing that package number, we got this transistor, and this one as well, and they look correctly. Whereas if you see a switch here, if I can find, oh, there it is. This is the switch, and I can't find the correct package to make it look nice like a switch, but we'll get there. What else? I've really renamed some things, and I've kept this component part of the circuit, which is a switch and the actual resistor to manage the switch, separate from this area here, because this one here we'll actually remove, and we'll drive it with a digital logic later on. I'll just double check the simulation again. LED on when switch is open. When switch is closed, the LED goes off. Seems a bit inverse, but it does work. Now let's go and construct this on our virtual breadboard. If you're a student or you've got the student edition, this breadboard is visible by going Tools, View Breadboard, or my little shortcut that I found is this little button here. So we'll drag these over here for now. That's our switch, we'll keep there. And we've got an LED. We've got a load resistor, which is going to go up here as well. The nMOS resistor, which is going to go here. And a switch resistor, which we'll use up here. So let's go and start connecting these things up. We've got a 5-volt power supply down here. Oops. Just zoom in a bit, see it there? That's the bottom line. And we'll connect that one up to there. And then we've got our ground, which is the second from the bottom. That one there is there. And while we're at it, connect it to the rest of the circuit. And we'll do the same for the power. Oh, that's a bit better. This is our load. And we'll just double check. We should have the drain here, which we do. So that drain. And we'll change the colours of the wires, and I'll tidy this up very shortly and go offline, but I'll quickly show you how to change the colours of the wires. Like this is 5-volt. This is the 5-volt one. White colour. Like them red. And grounds I like black. So what I'll do is I'll go away, I'll tidy all this up and get it looking very similar to the schematic diagram. Right, I've tidied up things a little bit now. So we've got our switch, which is not a good representation here, but when we're going to push a button or flick a switch, what happens is that when it's in the down position, we'll run through the transistor, through the switch and off to ground. When it's in the up position, we're going to be applying 5 volts to the nMOS up here, and that'll drive our circuit to drive our LED and switch it on and off depending on the state of the switch. What I didn't show you before is as you're placing components here, they change to the color green up here, and when everything's complete, the whole diagram will basically be green except for VDD and ground in this case. And there's an option up here called Drc and Connectivity Check. You can click that and it'll run it and tell you any errors that you found in your schematics or diagram. We can also run our simulation. Open and close the switch, and the LED will go on red when the switch is open, and when it's closed the LED will turn off, which is exactly the way we want it to operate in our one note here. When Q is equal to 1, the LED is on, i.e. if we get a 1 here, comes out here and switches the LED on, in this case when the switch is open. Learned a few tricks while doing this. I haven't done this for quite a while, so we'll save our work and I'll get all set up and we'll actually implement this on the actual breadboard. But just before we implement it on the breadboard, we'll go and look at their data sheets. So our nMOS This is the data sheet. You can take up to 60 volts direct current between the drain and the source. And the current, the maximum current it can take is 200 milliamps continuously, and up to 500 milliamps in pulse mode or very quick mode. And if we go down here, we've got the threshold voltage, and there's our 0.8 volts DC, and this is how much voltage needs to be applied before the gate is switched on. And here's our P channel MOSFET. It can take up to 60 volts between drain and source, and continuously it can take 280 milliamps. And it's where are we? Pulse drain current. The maximum can take it instantly at a fast speed is 4 milliamps. That's quite large actually. But pMOS is generally used to manage power. We can see some times to rise and how long it takes for this actual pMOS to rise and give us a 1, or fall and give us a 0. Just checking one other thing is, where are we? Threshold voltage. So it's switched off from around 1.5 volts to a maximum of 3.5 volts. We'll have a quick look at the switch that we're using. It doesn't look much here. It's a button switch, so when we press it down, we've got this schematic here showing. Yeah, that's about it. So let's start out our NI Elvis. Here it is here. The switch on the back switch. We've got a big ugly screen opening up, so we'll just tidy that up a bit. That looks a little bit better, and we'll start our digital multimeter. I'll drag it up to the top. Right, our digital multimeter, as you can see here, is connected, and it's connected down here, so we can take recordings. So we're recording DC voltage, we'll run that one. And at the moment we've got very, very small voltage. We'll switch the power board on. And I'll largen the window a little bit now. So what we've got is the switch. I'll put 2 switches down here. We're only using this one at the moment. We've got all our wires running across here from 5 volts and ground, and that's shown in this, shown here. We've got our nMOS up here, we've got our pMOS, we've got our resistor, and we've got our LED. The LED is on at the moment, and we're recording almost 5 volts. When we press the button, we'll go straight to ground, and we should receive very little voltage. So now we go to the gate over here. So this is the gate of the nMOS that I've connected to, and we can see that we've got 5 volts again. Press it, the LED goes off, and we get a small voltage hitting that gate at the moment. Release the button, the LED goes on. And we've actually basically built our circuit. Now we'll stop that one, and what we'll do is we'll run the simulation of this one. So we'll minimize this one. Run the simulation. When the switch is open, as it is now, the LED is on. When the switch is closed, the LED goes off, and we'll close the switch by pressing this button here. The LED goes off. We'll use this drive circuit, or load circuit, sorry, for other things coming up shortly.